All right, you can go.
Good to go?
Yep.
All right, my name is Devin Colon. I'm with Group 3. I'm the group leader this week for the refrigeration cycle. A heat pump can heat a space in winter or cool in space in summer. Either way, it's pushing heat from the low temperature source to the high temperature source. In the winter, the low temperature source would be the outside, and in the summer, the low temperature source would be the inside. The objectives would be to learn how to perform a thermodynamic analysis of a heat pump, because we all remember thermo, I'm sure, and loved it. And specifically, we want to measure the COP, the coefficient of performance, and describe its cycle in a pressure and enthalpy chart. We have some basic theories. This is derived from the first law of thermodynamics. All energy is conserved. Mess around with it a little bit, you get masses and enthalpies. And then we have our pH, our PV, and our TS diagram. Quick refresher, you got your compressor on this side. That's what we're always trying to make efficient to save us money and produce a lot of power and do what we want to do. The condenser on the top rejects heat to the environment. This will be where your throttling valve is, or your expansion valve. And then you have your evaporator, which is pulling heat in. Some more equations. This is how you find the COP using heat transfer and work input. This specifically equation right here would be for your compressor. You use the heat coming off the condenser and then the power going into the compressor, electrical, and that'll tell you your coefficient of performance or how well you're doing, the input to output of the system. Here's our apparatus. Everything you see up there with the ST is a temperature sensor. M's for manometers. We have the pressure sensors, the flow sensors. They're on all sides so you can run analysis. You see that you got the manometers and the temperature sensors on each side, on the bottom side of your evaporator, and on the output of the condenser. We have it on both sides of the compressor. You have a tank feeding water to both from the same reservoir, and you have your water pumps right here. And then this is your expansion valve right here. It's fed into the front of the evaporator right here, and I'll explain that in a second. So a thermostatic expansion valve. We want certain conditions to go into the evaporator. So what's coming out of the evaporator goes into the expansion valve right here. And it's going to affect this sensing bulb. It's filled with the thermodynamic fluid with similar properties to your refrigerant, and the pressure that it creates is going to open and close this diaphragm, allowing pressure to go into your evaporator as needed. As far as the procedure for test 1, we turn on the computer that controls the whole system. We switch on both of the pumps. To start off with, we're going to start with 5 liters per minute. We're going to switch on the compressor and turn that to approximately 40% of its output. We're going to let the system become stable. And then we're going to measure the indicated values on a table given to us in our manual. The values we want are going to be the power consumed by the compressor, the in and outlet temperature of the condenser, and the water flow rate into the condenser. Write these values down. And then after that, we're going to perform a second test. Once again, we're going to turn the computer on that controls the system. We're going to turn on both of the water pumps that feed the evaporator and condenser. We're going to switch the compressor on and once again set it to 40% of its capacity. We're going to adjust the evaporator side heat exchanger flow rate to be 3, 4.5, and 6 liters per minute. Let the system become stable for each one of those settings, and then record the values in the given table. And this time we want the pressure into the compressor, we want the pressure out to the condenser. We want the temperature in and out to the compressor. We want the temperature out to the condenser, and then we want the temperature out to the expansion valve. Predict the results. We're going to predict the coefficient of performance. Once again, based off of the electricity that we put into the compressor and the heat that we remove from the condenser. Best case scenario is 100% or isentropic, but that never happens because of entropy and loss to the compressor. If you remember from Dr. D's class, compressors are terribly inefficient, and the name of the game is to make those efficient, but it's just never going to happen perfectly. I predicted a COP of 70 to 85% based on an industry standard. Sources of uncertainty is going to be all your sensors, the temperature sensor, the flow sensor, the pressure sensor. Then we got references. Do I have any questions?